So today we are going to look at universal gravitation. It's called universal because gravity is everywhere in the universe that we know of. And it's kind of the same, the exact same that we see here on Earth. And this is the special form of gravitation called Newtonian gravitation, which is what Newton came up with whenever he came up with it. There is not currently the exact theory of gravity, which is now replaced by Einstein's theory of general relativity that covers gravitation. But for most purposes on Earth, this universal gravitation works. It's the 1 over r squared theory, which come in handy when you look at electric fields and magnetic fields in physics too. So it's important that you understand this. You will go over this a lot in physics 2 again. So this is essentially an application of vector addition, Newton's second law, because it's forces, circular motion, and conservation of energy. So let's get started. So the force of gravity, gravitational force, is given by G m1 m2 over r squared, where m1 and m2 are two objects. This is an object of mass m1. This is an object of mass m2, and they're separated by a distance small r. Then the force of gravity on m1 due to m2 is pointed towards m2. It's always attractive. And it's given by, in this case, if we call it F1, then it will be G m1 m2 over r squared. Now the force that m1 exerts on m2 will be along the line, and F2 will be G m2 m1 over r squared. Right? Okay, so it is two objects acting on each other, and we consider them pairwise. There's m1 and m2. So two objects together, one object exerts a force on the other object, and the other object exerts the force on one object. And what do you notice between these two forces? They are equal to each other. Right? It's just m1, m2, m2, m1. It's exactly the same thing. So these forces are equal to each other. And what directions do they point in? The opposite direction. So this is Newton's third law in action. So there is no external force acting on it. Newton's third law says that one object acts on the other object, then the other object will act equally and oppositely on the first object. Right? So this is Newton's second law in play, and Newton's third law in play also. So this is what we call mg. When we write a free body diagram on Earth, when you say mg, that is equal to F, force of gravity. And there is again the same thing as g times the mass of the Earth times the mass of your ball divided by the radius of the Earth squared. Right? So that little g is actually the gravitational field, which is given by g, mass of the Earth divided by the radius of the Earth squared. And so this is how you get Fg equals mg. Alright, so don't worry about that too much. It's just that gravitational field, we'll look at the field concept a lot when we do electric fields and magnetic fields in physics too. So this is what the gravitational force actually is. When we consider two separate objects in space, we do not worry about the mg pointing downwards. Unless specified that that object is on Earth, we can easily take one object, another object. Now this object can be the Sun, this object can be Mars. This vector force, you have to be careful, they always point towards the other object. Alright, the force vector points towards the other object. Gravitational force is always attractive. And why is that? It's way beyond this course. So we'll just take that for granted, that gravitational force is always attractive, pointing towards each other, taken pairwise, taken two at a time. Alright, so G is the universal gravitational constant, and that's equal to 6.67 times 10 to the negative 11th Newton meter squared per kg squared. Again, this is a force, so it's a vector. And so when you have more than one force, you have to add it up vectorially. Alright, so here's where vectors comes in. And this is again this principle of superposition that we saw in waves earlier. So now if we have three objects, let's have three objects, one object, another object, third object. One could be the earth, one could be the moon, the other could be the sun, who knows. And so if you're looking at object number 3, what is the net force on object number 3? Alright, now we draw a free body diagram. Net force, we always need to draw a free body diagram. And let's call this 2, let's call this 1. So one force that 2 exerts on 3, let's call that F on 3 by 2. And then there's another one. Let's call this distance d, and let's call this distance 2d. Right? So F32 is 2 acting on 3. F31 is 1 acting on 3. And then you add up the forces vectorially. So the F net on 3, let's just call it F3 vector, is F31 vector plus F32 vector. And that's the principle of superposition. All the individual forces get added together vectorially. Now, since this is a one-dimensional problem, you can simply add it or subtract it after you get the directions correct. So in this case, we know that F31, F32, but what is F31? F31 is G. If this is mass, let's take all masses to be M. Then we have M31, that's a distance 2d away. So 2d squared. Remember that this is not the same as 2d squared. Alright, that is wrong. 2d, all of it squared. That's the distance squared. 2d squared. Alright, and F32 is G. The masses are the same. M. This is also M. Divided by, now the distance is d squared. Alright, now they are both pointing in the same direction. If we take this as positive, then they're both pointing in the negative direction because gravitational force is attractive. So 2 attracts it towards itself, and 1 also attracts it towards itself. Also remember that 1 is farther away and the mass is the same, the distance is twice as much, so the force will be 4 times smaller. Right, so that arrow would be smaller. It doesn't have to be exactly scalable, but smaller would give me an indication that you understand what's going on. Alright, and now you plug these in. These both have negative numbers, values. Plug those numbers in and get the net. And the net again force will be pointed towards the left.